Dear students, today we will discuss about colligative properties. Before starting the colligative properties, we have studied in our chapter that solution of solid plus liquid. In the solution of solid plus liquid, vapor pressure of solution is less than vapor pressure of pure solvent. Vapor pressure of solution is less than vapor pressure of pure solvent. Or you can say vapor pressure of pure solvent is decreased when we add a non-volatile solute to it. Okay, and there are many properties of solution which are related to lowering of vapor pressure. Okay, and let's discuss that properties. So, what are the properties which are related to lowering of vapor pressure are relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. Okay, so these are the properties which are related to lowering of vapor pressure in a solution. And remember, all these properties depends on number of solutes only. Okay, so these are the properties that depends on number of solutes only. And now what is the colligative properties? Colligative properties now becomes like the properties of solution which are related to lowering of vapor pressure and depends only on number of solutes. These are known as colligative properties. So these four are colligative properties that we will discuss one by one today. So let's first start with relative lowering of vapor pressure. Relative lowering of vapor pressure. So we discussed that vapor pressure of solution is less than vapor pressure of pure solvent, or vapor pressure of pure solvent decreases on addition of non-volatile solute. Okay, why are taking here non-volatile solute? Because if we will take volatile solute, what will happen that the solute will also evaporate and it may create some problem. So we are discuss only about non-volatile solute. Okay, so our solution will be based on non-volatile solute plus volatile liquid. Okay, now the thing is that the vapor pressure decreases, but it decreases to how much? How much vapor pressure of solution is decreased as compared to vapor pressure of pure solvent? Okay, so let P naught be the vapor pressure of pure solvent and PS be the vapor pressure of solution. Students, here we can use Raoult's law to derive our expression for relative lowering of vapor pressure. How? Let me show you. First, say me what Raoult's law say is that vapor pressure of a component in a solution is directly proportional to mole fraction of that component in solution. And here our solution is a solution of solute and solvent. Okay, our solution is a non-volatile solute plus solvent. Okay, so now let's use this law. So here we have written vapor pressure of a component in a solution. Suppose we take our component as solvent. Means suppose you are taking the solvent as component. Okay, so what will be the equation? Vapor pressure of a component means solvent, vapor pressure of a solvent in solution that is this. Why? Because vapor pressure of solution is also vapor pressure of solvent in solution. The reason is, since we have taken non-polar X solute, it will not create any vapor. So whatever the vapor pressure of solution will be due to the vapor pressure of solvent only. So PS is the vapor pressure of solvent in solution. That is what vapor pressure of solvent in a solution. So let's write first PS is directly proportional to mole fraction of that component in solution. And I told we have taken our component as solvent. So mole fraction of solvent in solution. Mole fraction of solvent in solution. Let's write it like this. Okay. It will be PS equals to P naught into mole fraction of solvent. Why? Because if you remember it, while teaching the Raoult's law, that also at that time also we had used this term. Okay, where this is the vapor pressure of pure solvent. Okay, so this is the equation. And what we will do? Suppose these are the two terms, and if we subtract these terms from P naught in both the sides, what we will find is that P naught minus PS is equal to P naught minus P naught mole fraction of solvent. Okay, that implies that P naught minus PS equal to P naught 1 minus mole fraction of solvent. And I have told the total mole fraction of solvent plus solute is 1. So when we are writing 1 minus mole fraction of solvent, that is equal to mole fraction of solute. That is P naught into mole fraction of solute. Okay. So if we bring this P naught to this side, it will be like P naught minus PS whole divided by P naught is equal to mole fraction of solute. Okay. So this is our main equation. And see here, this P naught minus PS. What? This P naught minus PS is lowering of vapor pressure. Why? Because P naught is the vapor pressure of pure solvent. Okay, and PS is the vapor pressure of solution. So P naught minus PS is the lowering of vapor pressure. Why? Because vapor pressure of pure solvent is more and vapor pressure of solution is less. So when we deduct PS from P naught, that is lowering of vapor pressure. Means vapor pressure is lowered up to how much that I have asked. Okay, so this is lowering of vapor pressure. And when we divide this with P naught, that is vapor pressure of pure solvent, it becomes relative lowering of vapor pressure. This was the lowering of vapor pressure. And when we divide this with P naught, this whole term is called relative lowering in vapor pressure. Okay. So this is our equation. But what is mole fraction of solute? Okay. Suppose N is the number of moles of solute in solution and capital N is the number of moles of solvent in solution. So what will happen is that the mole fraction of solute is number of moles of solute divided by total number of moles, that is N plus N. Okay. So finally our equation is this: P naught minus PS by P naught is N by N plus capital N. Okay. So most of the people do what is that they neglect small n with respect to capital N, because small n is the number of moles of solute, that is very less as compared to the number of moles of solvent, that is capital N. So after neglecting this, what we write it as P naught minus PS divided by P naught equal to small n by capital N. So this is the equation that you can use. Okay, but if I say this is not 100% correct, I mean you will get the answer, but it is not 100% correct. So let deduce a equation that is 100% correct from this equation. Okay. Okay. So P naught minus PS divided by P naught equal to, actually we had n plus n here. Okay. Actually we had n plus n here, and if when we neglect this, we write this. Okay. So our original equation was this. Okay. If we reverse it, P naught divided by P naught minus PS. If we bring that 1 to the left hand side, okay. Again, if we will reverse it, P naught minus PS divided by PS is equal to n by n. Okay. So this is the final equation that we can use for relative lowering of vapor pressure type of question while solving, where P naught is vapor pressure due to pure component, whereas PS is vapor pressure of solution. Small n is number of moles of solute in the solution, and capital N is number of moles of solvent in the solution. So this was all about relative lowering in vapor pressure. Students, so we finished relative lowering in vapor pressure, and our second colligative properties is elevation in boiling point. Students, first tell me whether vapor pressure depends on temperature or not. My question is whether vapor pressure depends on temperature or not. And the answer is yes, vapor pressure depends on temperature. Okay, why? Because if we increase temperature, what will happen? That vapor pressure will increase. Because let's take an example. Suppose this is a liquid. Suppose this is a container where this liquid is kept. Okay, so what happens when we increase the temperature? Means we are providing energy. What happens? The solvent molecules that are present on the surface, after getting energy, leaves the surface and form vapors. Okay, so when we increase the temperature, more number of solvent molecules will leave the surface. As a result, more number of vapor will be generated. That means vapor pressure will increase. Okay, so when we increase the temperature, vapor pressure also increases. And what happens when we go on increasing the temperature at a particular temperature? That much a sufficient amount of vapor will be created, so that the pressure created due to that vapor will be equal to atmospheric pressure, that is 1 atm. And when the vapor pressure is equal to the atmospheric pressure, that temperature is called boiling point. That means at boiling point, vapor pressure of solvent is equal to atmospheric pressure. Okay. Now students, let's draw a graph to understand this elevation in boiling point. What is that? So let's take vapor pressure in y-axis, temperature in x-axis. So now we discussed when temperature increases, vapor pressure increases for a liquid, or when temperature decreases, vapor pressure will decrease for a liquid. So first we are taking a liquid where vapor pressure is decreased when temperature is decreased. Here temperature increase, here temperature decrease. So when temperature decrease, vapor pressure is also decreasing. Okay, so this is the curve for a solvent. Okay, now you guys know that vapor pressure of solution is less than vapor pressure of solvent. So if we draw a curve for solution, then what will happen? Its vapor pressure will be less than vapor pressure of solvent. So suppose this is the curve for solution. You can see here the graph for vapor pressure of solution is less than vapor pressure of solvent. Okay. Now what to do is that suppose now we want to create same amount of vapor pressure in both the container. Means suppose here we have taken only liquid, and suppose we take another container where we will take solution. Okay, so here liquid plus solute is there. So this is solution and this is liquid. Suppose we want to create same amount of vapor pressure in both this container. So now tell me whether we need same amount of temperature or different amount of temperature. And the answer lies within this graph. We will create same amount of vapor pressure, means vapor pressure will be same. So when vapor pressure will be same, the respective temperature is like this. Okay. So this is here you can see here that when we want to create same amount of vapor pressure in both the container, we need more amount of temperature in case of solution. Okay, we need more amount of temperature in case of solution, whereas in case of solvent we need less amount of temperature. And if now I say that suppose now I want to create a vapor pressure of 1 atm. Okay, I want to create a vapor pressure of 1 atm in both the container, that is equals to atmospheric pressure. Okay, so if I want to create a vapor pressure of 1 atm, the temperature that will be required to create this vapor pressure will be known as boiling point temperature. Boiling point temperature. Okay, so now suppose I want to create a vapor pressure of 1 atm, and the respective temperature will be boiling point temperature. So now from this same graph you can see that boiling point of solution is more, whereas boiling point of solvent is less. So boiling point of solution is more than boiling point of solvent, that is pure. Okay, and if we take an example, suppose I say that I take 50 ml water in this container, then the temperature that I need to give this container is what? Okay, let's see. Here suppose 50 ml water plus sugar. So that means to boil this water present in this container, the temperature that will be required will be less as compared to the temperature that will be required to boil this solution present in this container. Okay, so boiling point of solution is greater than boiling point of solvent. Now, what is elevation in boiling point then? Then now, elevation in boiling point is the extra amount of temperature that we must supply to boil the solution is known as elevation in boiling point. That is the extra amount of temperature needed to boil the solution. Okay, so this is elevation in boiling point. And now let's make a mathematical equation. So suppose this Tv naught is boiling point of solvent and Tv equals to boiling point of solution. So boiling point of solution is mole. So elevation in boiling point is Tv minus Tv naught. That is elevation in boiling point. Okay, we can write it as del V. Okay, and it has been seen that delta V is directly proportional to M, where M is molarity of the solution. What? M equals to molarity of solution. And what is molarity? Molarity is number of moles of solute present in 1 kg of solvent. Okay, moles of solute dissolved in 1 kg of pure solvent. Okay, so elevation in boiling point is directly proportional to molarity. That implies that del V equals to, it can be Kv into M. Suppose we write this, where this Kv is known as boiling point elevation constant. Kv equals to boiling point elevation constant, or it is also told that this is ebullioscopic constant. Okay, ebullioscopic constant. Okay, so this is the final equation that we can use for while solving any question from elevation in boiling point. That is delta V, or we can write like Tv minus Tv naught is equals to Kv into molarity. Okay, and if I define molarity, that I told that moles of solute dissolved in 1 kg of pure solvent. Okay, and what is moles of solute? Suppose W1 is the weight of solute, M1 is molecular weight of solute, and W2 is weight of solvent in gram. Okay, so if weight of solute is given, if molecular weight of solute you know, and if weight of solvent also you know, then we can calculate elevation in boiling point. So what will be the equation? Tv minus Tv naught, that equals to Kv into molarity, which is moles of solute. What is the moles of solute? W1 divided by M1, weight of solute divided by molecular weight of solute, that is moles of solute, whole divided by dissolved in 1 kg of pure solvent, means weight of solvent. So we have taken W2 gram of solvent, that will be equal to W2 divided by 1000. I am dividing it in 1000 because I have taken it in gram. Okay, I have taken it in gram and we need it in kg. Okay, so the final equation will be del dV equals to kV into so this is your final equation to deduce elevation in boiling point for delta T is elevation in boiling point that equals to kV, that is boiling point elevation constant, W1 weight of solute, M1 molecular weight of solute 1000 and W2 is weight of solvent. So this was all about elevation in boiling point. So students, let's start the third colligative properties, that is depression in freezing point. So first tell me, what do you mean by freezing point? Freezing point of a substance is the temperature at which vapor pressure of that substance in liquid phase is same as the vapor pressure of that substance in solid phase. Let me write that. Freezing point is vapor pressure, the temperature at which vapor pressure of liquid is equal to vapor pressure of solid for a particular solvent. Okay. Again, we have already discussed when you increase the temperature, the vapor pressure increases, and similarly, when you decrease the temperature, the vapor pressure decreases. So for a liquid, when you decrease the temperature, vapor pressure also decreases. But here, and another thing that is very much important, when we go on decreasing the temperature below a particular temperature, what happens? The liquid solvent got freeze. Okay, to make you understand, let me draw a graph. Okay, so let's draw a graph here. Here in this side vapor pressure, and in x-axis take temperature. Okay, what I told you that when vapor pressure of a liquid decreases, when the temperature decreases, the vapor pressure also decreases for a liquid. So when we decrease the temperature, vapor pressure so decreases. Then what happens? When you go beyond a certain temperature, go below a certain temperature, the liquid solvent got freeze. Suppose when you go below this temperature, the liquid solvent or the liquid got freeze. Suppose this is liquid solvent, and below this temperature it got freeze. Okay, so this is the frozen form, that is we can say that solid solvent. Okay, so below this temperature the solvent has got freeze. Okay, again we know that vapor pressure of a solution is less than vapor pressure of solvent, and again when we decrease the temperature of the solution, its vapor pressure also decrease, but at a particular temperature that solution also got freeze. So make it like this. Okay, so for a solution, when you decrease the temperature, the vapor pressure is decreasing, and at a particular temperature it is again getting freeze, means the solution is getting solid. So this is the curve for solution. So at this point it is getting freeze. Suppose this temperature is T F naught, this is T F. We'll discuss it later, but Now from this graph you can see that what I told, freezing point. Freezing point is vapor pressure of liquid is equal to vapor pressure of solid. So for this liquid solvent at this point or at this temperature, the vapor pressure of this liquid solvent is same as the vapor pressure of solid solvent. Okay, so this is the freezing point. This is the freezing point for solvent. And about the solution, when we decrease the temperature, at this temperature it got freeze. So this is the freezing point for solution, because at this point the vapor pressure of this solid solvent and the vapor pressure of the solution are equal. So this is the freezing point for solution and this is the freezing point for solvent. Okay, now what is depression in freezing point? Okay, what is depression in freezing point? Now depression in freezing point is that difference in temperature. That difference in temperature between the freezing point of solution and freezing point of solvent. So first write from the graph, freezing point of solution is less than freezing point of solvent. So the difference between this freezing point of solution and the freezing point of this solvent is known as depression in freezing point. Suppose you told it delta T. Okay, then this delta T is freezing point of solution. What you have taken? Solution for solution, it is TF. Okay, so actually freezing point of solution this is TF and freezing point of solvent this is TF naught. And when the difference between this temperature is delta T and that is equal to depression in freezing point. It means that again we need to drop the temperature by this delta T amount, to freeze the solution. Okay, because freezing point of solution is low. And if I give an example, you will understand it properly. Suppose we have water and it freezes at 0 degree Celsius. Okay, and if we take a solution of water, suppose sugar solution, that means the sugar solution is not going to freeze at 0 degree Celsius. Rather, it will freeze at minus 2 degree Celsius or minus 4 degree Celsius or whatever, but below 0 degree Celsius. Okay, less than 0 degree Celsius. And the difference between this temperature is known as depression in freezing point. Okay, so freezing point of solution is TF and freezing point of solvent is TF naught. And which is greater? TF naught is greater. So if I write the difference between them, that will be equal to, this is greater, so let's write this first, TF naught minus TF. This is what? Depression in freezing point. Okay. And it has been seen that delta T is directly proportional to M, where M is molality of the solution. Okay, where M is equal to molality of solution. And what is molality? Molality is number of moles of solute present in 1 kg of solvent. Moles of solute divided by weight of solvent in moles of solute by weight of solvent in kg. Okay, so let's write this first. Suppose this will be now delta T equals to KFM. Let's write this like this. Now what happens? This Kf is a constant which is known as freezing point depression constant. What Kf is? Freezing point depression constant, or it is also called hygroscopic constant. Hygroscopic constant. So, using this formula, you can solve the problem of freezing point type of question. But if we elaborate it again, then it will be like, suppose W1 is weight of solute, M1 is molecular weight of solute, and W2 is weight of solvent in gram. So what is molarity? Molarity is W1 divided by M1, that is moles of solute, and 4 divided by weight of solvent in kg, and here we have taken weight of solvent in gram, so W2 divided by 1000 will be in kg. So if we put this here, it will be like delta T is equals to Kf into W1 divided by M1 into 1000 divided by W2. So this is the final formula for depression in freezing point, where delta T is depression in freezing point, where Kf is hygroscopic constant, and W1 weight of solute, M1 molecular weight of solute, and W2 weight of solvent. So using this formula, you can calculate depression in freezing point in a question. Okay. So now discuss about the fourth colligative property. Okay. Now discuss about the fourth colligative property. What is the fourth colligative property? Osmotic pressure. Okay. Osmotic pressure. Okay. So before we understand what is osmotic pressure, let's understand what is osmosis. Okay. What is osmosis? The continuous flow of solvent molecules from lower concentration site to a higher concentration site through a semi-permeable membrane is known as osmosis. Okay, to make you understand this clearly, let me draw a diagram. Suppose let's take a container. Okay, and this is the semi-permeable membrane. Suppose in this side we have taken the solvent, and this side we have taken the solution. Okay, so this is solvent and this is solution, means we have solid particles also present. So you say concentration of solvent is low or concentration of solution is low. Obviously concentration of solvent is low. Why? Because in solution we have added solid particles also, so it has a higher concentration. So this side is low concentration and this side is high concentration. And what I told is, when the continuous flow of solvent particles from this side, from the lower concentration side to higher concentration side, so the flow of solvent molecule from this side to this side is known as osmosis. And can you just tell me, this osmosis will take place till when? Okay, this will take place until the concentration of both the chamber is equal. Okay, when the concentration of both this chamber will equal, this osmosis will stop. Now let's discuss what is osmotic pressure, because now we come to the point. So solvent molecules are going from this side to this side, or from lower concentration side to higher concentration side. Suppose we want to stop it. Okay. Suppose you want to stop it, then what you have to do? Can you say? What you have to do? We can apply pressure in this chamber. Okay. When we increase the pressure in this chamber by compressing this to a smaller volume, what will happen? Pressure in this chamber will increase and our solvent molecules is passing from this chamber to this chamber. So it will prevent it. Okay, we are giving the pressure here, so it will prevent it. So that is the osmotic pressure. Then what is the osmotic pressure? It is the pressure, it is the minimum amount of pressure that you require to stop the flow of solvent molecules from lower concentration site to higher concentration site is known as osmotic pressure. Okay. So better you write it, osmotic pressure. This is the minimum pressure required to stop osmosis, you can say, because osmosis is flow of solvent molecules from lower concentration site to higher concentration site. So if we want to stop osmosis by giving a pressure, that pressure will be the osmotic pressure. And it has been found that, okay, suppose we take osmotic pressure by the symbol pi. So it has been found that the osmotic pressure is directly proportional to concentration of solution and temperature. Okay, so pi will directly proportional to concentration of the solution and temperature. Why concentration of the solution? Because if concentration of this solution will increase, okay, if concentration of this solution will increase, more amount of solvent molecules will flow from this side to this side. Okay, so we require more pressure to apply to stop this osmosis process. So it is said that if concentration increases, we require more amount of osmotic pressure. Okay, so if we replace it, pi equals to CRT, it will be pi equals to CRT, where R is gas constant. Okay, R is gas constant, and you know pi is osmotic pressure, and C is what? Concentration of solution. And what is concentration of solution? Moles of solute per unit volume. Moles of solute by volume of solution. That you can write as N by V, where N is moles of solute and V is volume of solution. So what will be the final equation? Pi equals to N by V R T. Okay. In place of concentration, we wrote N by V. So this is the final equation.